information about your test. It's graded. I will be putting it together with your homework, and that will then become sent to you as an email. And the email I'm using is the one that you used on WebAssign. It's too much work for me to take, you know, fredisgreat@yahoo.com and try and figure out what your real student email is. So I prefer not to do that, but since it's the only thing available, I will do it. So if you know that that's an email address that you've used to log into WebAssign, that's where you're going to have to go to get your grade when I'll send it. Otherwise, it's a lot of you, thankfully, have got your school email used, and that's going to be really good because then it's easy to communicate back. The test, I wouldn't say the test was difficult, but I would say that one of the problems with the test is that because there were so many multiple choice questions, there really wasn't any opportunity for a lot of questions for you to get much extra credit, and that is unfortunate. So all you need to do is pick 3 when it should have been 2, and you could have lost 5 or 10 points, boom, right off the bat. So when you get your grade, it's just going to be homework in your midterm. Your final grade will be better than that, and the reason why it would be, but I haven't done it yet because I'm only going to do it once, is that remember 20% of your grade is for participation. So if you've been coming a lot, that's going to boost your grade up. And some of you got a couple of % extra credit because you did that special project at the beginning, like the Canvas thing. So whatever number it says, if you want a rough guide, if you've got really good attendance, which means you've only maybe missed a couple of days, right? That'll get you your grade. So that would be that would probably add a very rough guide about 5% onto your grade. So if you get a grade and it looks like a 3.2, you'd probably be a 3.7 when we add participation onto it. So just so you get a better feel for what a realistic number is. I'm not doing your attendance right now. It's a horrendous job, so I only want to do it once. I don't want to have to do it twice. So I will do the attendance on the last week when we're going to be doing your final and so on. Okay, let's get started. A new guy in town, a new chapter. We're only going to do 7.1 today. I'll be doing the other 7, God, what's that, 7.2 on Friday. And then next week, we'll be doing the other guys, right? And so that's kind of how that's going to work out. So what's the first one? Estimating the mean of a population when sigma is known. Right, well, I'll give you a little bit of background. You've got a population. And let's suppose that population, you're interested in finding its mean. And let's say, just for argument's sake, we wanted to know the average height of people who live in Scotland. Adult males. Right? And we get the answer that it's 67. Now, the only way we could really get that answer would be to measure the height of every Scottish adult male in Scotland. So we could pretend we got that. And let's pretend that we also got a standard deviation, and it was 5. Now, when you use those numbers, you recognize that means population mean, population standard deviation. So if you imagine that's the truth. Now, let's think of real life. We actually don't know the average height. Right? That's more realistic. But we'd like to estimate it, right? We'd like to get a guesstimate, right, of what it would be. And what we do is we do a simple random sample. And this simple random sample, say, size 100. And we find the mean. Do you think the mean of my sample 100 is actually going to be the 67, the real answer? In real life? No. Won't it be 68, 64.5, 69? But it should be pretty close, you would hope. and pretty close most of the time. But let's just say, for argument's sake, that we got 65. So far, so good. Wouldn't it be nice if there was a way that we could use this guy and this guy to give you an interval of estimates, right? Saying we're 90% sure that the right answer is between this low number and this high number, or we're 99% sure, or we're 95 or whatever. And the answer is, there is a way to do that. There is a formula that will allow you to find what is called a confidence interval. And that's what 7.1 is going to be about. Most of it, a good chunk of it, is going to be about finding this thing called a confidence interval. Now, a confidence interval has a number associated with it. How confident are you that whatever this interval ends up being, that the real answer is somewhere in that interval, right? That's what a confidence interval is. Well, there is a fixed amount of standard values for that fella. And I'm making sure I got my right numbers. Yeah, here we go. You can get an 80% confidence interval. You can get a 90% confidence interval. You can get a 95% confidence interval. And if you wanted to be really, really sure, you can even get a 99% confidence interval. Now, for each one of these confidence intervals, there's a magic Z number. So when you're making an 80% confidence interval, the magic Z number is called Z.8, and it's equal to 1.28. It's always 1.28 when you do an 80%. When you do a 90% confidence interval, it's 1.645. If you do a 95% confidence interval, you get 1.96. And if you do a 99% confidence interval, you have to use the magic number 2.58. So you probably want to write them down on a piece of paper somewhere, because you're going to be using these guys a lot during 7.1. Actually, you'll be using them a lot during most of chapter 7. So I haven't told you what the magic formula, this thing called the confidence interval, is. Okay. Which one of these four do you want me to do? Give me a confidence interval to create. Pick one at random.
95.
95.
Okay, so we are going to do a 95% confidence interval. The formula for getting that is X bar, so a 95% confidence interval. It's X bar plus or minus, because you're going to add and subtract from this mean, the sample mean. The magic number for 90%, 95%, and I'll put it in red just for emphasis, is 1.96. Multiplied by sigma divided by the square root of n. So in this fictitious story, 65 plus or minus 1.96 sigma divided by the square root of 100. And so we're now going to rely on calculators. Just going to get this bit. 1.96 times 5 divided by the square root of 100. And the answer I get is what? 0.98. Now, if you add and subtract this guy from that, tell you what, can we just, to make my story easy, can we pretend that's plus or minus 1, because it's pretty close to it, right? 64 to 66. That is my 95% confidence interval. So I am 95% sure the average height of Scotsy adult males is in that range. Wait a minute. In your fictitious story, you told me the real answer was 67. How come it didn't work? Well, the reason it didn't work is, isn't this a 95% confident? Doesn't that also mean there's a 5% chance it's totally wrong? And guess what? This was one of them. And you know when they do polls on TV and they tell you a Republican is going to win this state or a Democrat's going to win that Congress or whatever it is, you know that they get them wrong 5% of the time, 10% of the time, 20% of the time. So can you imagine if you were doing 5 states and you were going to predict who the governor winning was, but you used this thing to do it? Wouldn't one of your 5 predictions be wrong and the other guy wins? And when you do general elections, haven't they predicted one person was going to win before the election, and then the other person ended up winning? So what is happening there isn't that the math is wrong. What is happening there is that you have just been unlucky and got a sample that told you an incorrect conclusion, right? You got one of the 5% wrongers. Now, how do you get lots of mistakes? I suspect very strongly that a lot of the polls that we're dealing with right now are maybe using 90% confidence. And so if there was 10 presidential elections and you were using a 90% confidence interval, aren't you going to get one of them wrong? I mean, just by averages. And if you're a really unlucky person, could you get 2 of them wrong? So when you see TV and they say the latest poll, by the way, a poll's just a sample where you ask people how you're going to vote, right? It's a sample. They say, oh, the latest poll, John Smith's going to win Kentucky. Well, you bear in mind that that does not mean John Smith will win Kentucky. That means you're 90% sure he is or 95% sure he is, but you could be wrong. And you will be. Now, this is silly, but just to give you an example. Do you notice that the highest one I've got here is 99%? Doesn't that still mean 1 in 100 times I'm going to be wrong? Statistics does not tell you a guaranteed interval, except in this one very silly situation. I am 100% confident that the average height of a Scotsman is between 0 and infinity. And that's the only interval that you can ever be 100% sure of in statistics. So if anybody says it's 100% certain somebody's going to win Kentucky, they're lying. Bottom line, they're just telling you a lie. Nothing in statistics ever says 100% sure, because you're basing your estimate on a sample of people. Couldn't you just get unlucky and ask the, people with a particular perspective that's different from the average kind of person? Right, are we comfortable with this process? How to create a confidence interval based on these magic numbers. So let's do the next one. Let's do IQ of French people. Now, I happen to know that the standard deviation of IQs is 10, right? We got that way back in the day. We know that for sure. And I'd like to find the IQ of Frenchmen. So I took a sample of 20 Frenchmen, right? A nice random sample, but only 20 Frenchmen. And I am going to get a 99% confidence interval. And those Frenchmen that I went and asked, their average IQ was 104. So that's actually better than the world average, right? The world average is 100. So I wonder if that's going to come out with anything interesting. Well, the formula, X bar, plus or minus 2.58. Sigma over root n. X bar is 104, give or take, 2.58 times 10 divided by the square root of 20 people. And this guy is 104. Oops, wrong one. I want to do this first. 2.58 times 10 divided by the square root of 20. And the answer I get is, let's just call it 5.8. So it's 104, need more room. It's 104, give or take 5.8. So in your homework, there'll be a box that looks like this, lower limit. Then underneath it, typically another box where you put the upper limit. And then a third one, which I haven't spoken about yet, but I will. It's called the margin of error. If you take 104 and subtract that, you get 98.2. That's the lower limit. If you add 5.8 to that, you get 109.8. This guy here is called the margin of error. Right, this bit of the answer, right, this 5.8, that's called the margin of error. So when I like to see this differently, because I'm a kind of visual person, can you imagine that 100 is here, and about here is 109.8, and over here is like 98.2. And what you're saying is that based on that sample, we are 99% sure that the average IQ of Frenchmen is somewhere between 98 and a bit and 109 and a bit, right? Now that's a big range, isn't it? That's a lot. 5, almost 6 either side of the mean. But at least we're 99% sure. Now, from this information, we can sometimes also get some other conclusions. So based on this little picture here, I can say that I am 99% confident that the IQ of Frenchmen is less than 110. Because isn't everybody in that interval less than 110? And I'm 99% sure of that, right? I could be wrong, but I'm only going to be wrong, what, 1 in 100 times, right? Not that often. Can I also say that the average IQ of Frenchmen is definitely bigger than 98? You know, it's just another way of putting that information together. What I can't say for sure is that the average IQ of a Frenchman is 104, or that the average IQ of a Frenchman is even 100. Because what this interval says is that any number between there and there, any of them, could be the right answer for the entire population of Frenchmen, right? It could be 98.3, just as likely as 100, just as likely as 107.9. So we put no emphasis on actually that number, or at least no more emphasis than any of the other numbers that it could have been. We cool? Now, next one I'm going to show you is a kind of truism, a general property. So we have a bunch of ducks, because I want to just pretend to get a new story, and we do a sample of 100, and the mean of that sample of 100 comes out as 3.1 pounds. So on average, these ducks weigh about 3 and a bit pound, right? I then do a sample of 1,000, and just by sheer luck, because this is to try and emphasize a truism, something that's true all the time, just by sheer luck, can you imagine that the average still came out as 3.1? Now I'm going to do the same confidence interval for these two. And I can do anything you like, 90, 95, 99. Let's do 90% confidence interval. And I'm going to do it with a sample size of 100. And then I'm going to redo it again, a 90% confidence interval. But I'm going to use the numbers from the 1,000. And let's just say that sigma is 2, right? So far, so good. Before I do this, do you think the confidence interval for both of these is going to be the same size? Or do you think William's going to be bigger or smaller than the other? What's your gut feeling? That interval is going to be the same as that interval that's bigger or less?
1,000 to be bigger.
So you think the interval on 1,000 is going to be a bigger interval? Is that what you're thinking? Okay. Anybody think the opposite, that 1,000 might make a smaller interval? Ethan's nodding like he would be in that bunch, right? Well, let's find out.
Sorry, Professor, I have a question.
Yes, Raina.
The textbook is calling confidence level. What
Yeah.
you have in your notes as confidence interval.
Yes.
What is the difference between both?
None whatsoever. They just use confidence level.
Okay.
Well, let's check that out a little bit. Confidence interval is talking about the interval itself. Confidence level is more talking about the 90%. But I mean, that's just semantics. You're doing the same thing. Right. So we have an X bar plus or minus one, forget about the color scheme now, 1.645 times sigma over the square root n. That's going to be 3.1, give or take 1.645 times 2 divided by the square of that fella, little squiggly line. I'll go over here and try this fella out. 1.645 times 2 divided by the square root of 100, which I know is 10. So that's 0.329. Darn it, I should have called that 3.3. Can I call it 3.3 just to make life easier? So 3.1, see what the lower limit is going to be. 3.1, take away 0.33. The average weight of these ducks might be as low as 2.77. It could be as high as 2.43, and that's my confidence interval.
I have a question.
Yes.
So in the previous one, you divided the square root of n by the whole thing, the like point number. Does it matter if you multiply the top number first, or
No.
okay?
So you can multiply those two first and then divide by that. You can take this guy times that divided by that. As long as the 2 in the top are multiplying the 1 in the bottom is a divide. You could actually do them any order you like. It should be the same answer.
Okay.
Right, let's try this fella. I won't write the formula down. It's going to be 3.1, give or take 1.645 times 2, but this time 1,000. So that's going to be 3.1, give or take whatever that ends up being. So 1.645 times 2 divided by the square root of 1,000. And that's 0.1, which means it's 3 to 3.2. Well, let's visualize what that looks like. So imagine there's 3, right? And there's 3.1, 2, 3, 4, there's 3.5. And there's 2.9, 2.8, 2.7, 2.6. There's 2.6. 2.77 is about here, and it finishes at 3.43, which is about here. So somewhere between here and here is the true answer for the average weight of those ducks. And that was when we did the sample of 100. Now, if we do a sample of 1,000, the range we got was 3 to 3.2. Can you see that the interval is much smaller when it was 1,000 compared to when it was 100? Now, what that is telling us, I think if you think it through, it makes sense. Would you agree that a sample of 1,000 is more likely to give you an accurate answer than a sample of 100? And an accurate answer would mean that you should be able to judge where the right answer is in a smaller area, right? You're 98% sure it's in this area rather than this huge, could be anywhere area. So that is a truism, and what I mean by that is that as n gets larger, the size of the interval gets smaller. So can you imagine if you doubled the number in your data set, wouldn't you probably shrink the size of your confidence interval? Just look at the margin of error, 0.33, 0.1. Isn't that at least 3 times smaller, right? More condensed. Any questions about that? Are we good? Okay, I'm going to go over some homework questions in a few seconds. Why don't we take attendance right now? So say hi, get your attendance. Hope you know that attendance is measured in this little time slot. So if you turn up and then go and have your dinner and then come back when the lesson's over, you will have missed that high and therefore you will not get attendance. Of course, if you're already left and got your dinner, you never heard that. But that's how it works. So we are now going to look at some 38, good number. Basic, good. Right now you should be looking at question 6. Does that look right? Okay, good. So Alan Humming's bird. Evidently it's got a Latin name. I know this because of my other class, but I didn't know it before I seen this part. That evidently there's a little hummingbird called Alan Hummingbird, and it's tiny. I mean, absolutely scarily tiny. And they're probably rare. From what I can judge by the numbers, can you imagine a big fat bumblebee? That's kind of the size of this bird. Right? You could almost swat it like an insect. Don't. The hummingbirds are beautiful. In this story then, he did a sample of 13. And the standard deviation is equal to 0.34. And here's an assumption that I haven't talked about yet. In every question that we've been doing so far, we have assumed that the population was nice and normal, right? It wasn't a weird, skewed thing. And that assumption is pretty much taken for granted in all these questions. So it should and would always have to be normal. So he took a sample of 13 and he got that the average weight of his sample was 3.15 grams. Have you any idea how little that is? Do you know there are 1,000 grams in a kilogram? Right? So if you take 2.2 pounds, right, and you divide it by 1,000, and then you times it by, oh, let's be generous, 3, and then you multiply that by 16. It weighs just over 0.1 of an ounce. Has anybody even seen this thing? I don't even know which country maybe it lives in, you know, the Amazon jungle or something. Right, so we got all the key information. What we're being asked to do now in this question, in question A, is to find an 80% confidence interval. Do you see how they do the, oh, they call it confidence interval now. Go figure. We're going to do a lower, we're going to do an upper, and we're going to get a margin of error. And then I'll return to this question. So just to give you a feel for what does this, you know, this question look like. So here goes. Now an 80% confidence interval. It's going to be the mean plus or minus 1.28 sigma over root n. It's going to be 3.15 grams, give or take 1.28 times 0.34 divided by the square root of 13. Now that sample size is tiny, but we can still use it. So 1.28 multiplied by 0.34 divided by the square root of 13. Now what's going to make this good is, can you imagine when you do this in your final, you'll be able to show me lots of working. So if you make a mistake, you'll be able to get a lot of points. In the test, you use salt, but unfortunately, if you don't read off the right number or do the left or the right, it comes out weird. So what I'm looking at here is 3.15, give or take 0.12. The margin of error is this guy. The lower limit is what you get if you take this away from that. And the upper limit is what you get if you add it. Right, does the format of that question kind of seem obvious now? What you have to do and where you put the numbers? Okay, so let's return to that and see what the rest is. So lower limit 3.03, upper limit 3.27, margin of error 0.12. Now, what conditions are necessary to allow us to do this? Normal distribution of weights, right? It has to come from a normal population. That's what that means. There's one more in this list. Not two, but just one. Who's the other choice? The other thing that must be true.
The very bottom one.
Sigma is known. Do you notice the formula had sigma in it? If you don't tell me sigma, I can't do the question, right? That's basically it. Now you might think n is large. It's not necessary to calculate an interval with a large n. It's better if you do, but can't you do it with a small n, a huge n, or any other value of n? It's not a guaranteed thing. There's the interpret bit. So far, so good. And now a new question. Find the sample size. Find n that's necessary for an 80% confidence interval to have a margin of error. We use E for margin of error. Well, this textbook does. Most textbooks call it MOE, but E will do, of 0.11. So I'm going to write that down and show you how we find what the sample size needs to be. And that's pretty much, once we've done that, everything that we need to do. All we're going to do after that is some practice. Okay. Now, we're still doing an 80% confidence interval, right? So the formula that we're going to use for calculating n, it's the magic number, in this case, 80%, times sigma divided by E, and the whole thing is squared. Now, the magic guy is 1.28. Sigma in this question was 0.34. And E was 0.11. And then you square the whole thing. If you want to do that in the calculator, this would be the way I would do it. I would use bracket. So go bracket, do 1.28 times 0.34, divide it by 0.11, close the bracket, and then just square it. And you're going to get a decimal answer, 15.65. In any question where it says, what sample size do you need to get this margin of error, you don't use the decimal. Would you agree that you ask 15 people or you ask 16 people, right? You don't ask 15.65. These answers always have to be a whole number. They won't even tell you that. You'll just have to assume that, or they're assuming that you know that. So what would be the sample size? How many hummingbirds should I need to look at if I wanted this margin of error? It's not a trick question. What would
16.
You do? Yeah. Now, would you agree that to the nearest whole number it is 16? Right. So here is, it's not a trick question, but here is something that will happen. Can you imagine a different question where you got that? You would think that you round off to the nearest whole number, but you don't. You round up all the time. So this guy would be 15. So let me try and give you an argument for why you want 15. In fact, could maybe someone else give me the argument instead? Why would you do that? Erica?
It has to be more than 14.
Just to be safe, right? Yeah, I agree. So you always round up, it has to be more than 14. Well, if it has to be more than 14, it has to be 15, right? That's the next number after 14. That kind of argument. That makes sense. It doesn't make sense right now. Always round up. When you get a question that says, what sample size do you need to get a particular margin of error? Use the formula, whatever the answer comes out, round it up. Okay, so I'm going to make up my own question again, but it's basically going to be just like those ones. You're going to have a sample It's going to have a certain size. You're going to know sigma, and you're going to find a 90, 95, 99% confidence interval. So I'm going to pick on American football players. IQs are 10. We get a sample of 50 American football players, and he found out that their average IQ was 92. And we would like a 95% confidence interval of what the average IQ of all American football players are, right? So imagine this sample of 50, just 50 out of everybody who plays American football. Well, pretty straightforward. Well, a 95 is going to use a 1.96 as its magic number. In this case, 92, give or take 1.96 times 10 over the square root of 50. And that gets me 92, give or take 1.96 times 10 divided by the square root of 50. And the answer is, let's call it 2.8. So the margin of error is 2.8. Lower limit, upper limit. Take that away and you get 89.2, add it, and you get 94.8. And me personally, I like to see that as an interval. So we are saying that our best prediction is that the average IQ of American football players is somewhere between, what, 89 and 95, very roughly. And we are 95% confident that the right answer is somewhere in that range. Could I write a newspaper article and say, American football players are below average IQ, which is another way of saying are below 100? Is that evidence that they're below 100? Is it? Is this evidence, if this was true data, that they're below 100?
Yeah.
Yeah. Aren't all of those less than 100? Now, if you want to be an optimist, couldn't you say that their IQ is definitely better than 89 on average? So this is the kind of evidence that you can sometimes use in the scientific world. You create an experiment where you do it 50 times and you come up with, maybe the experiment is you're trying to find the velocity of an electron, right? Something that's really hard to get to grips with, but you're trying to do it. Can you imagine you might do the experiment 50 times and you got whatever that number here is as your average? Won't you then be able to put a kind of range of what the true speed of an electron is? Actually, I think electrons only travel at one speed, but whatever that would be, maybe that's not true. But light, for instance, does travel at one speed. It travels at the speed of light. It's a fixed value. So you would be able to use that to put range. You could even say things like, well, I know for sure that it's not 100, right? But am I 100% sure? Nope. Isn't there a 5% chance that football players have a really high IQ, right? On average, it might be on 5. Because this is only 95% of the truth. Are we good with that? Imagine somebody got data on the governor's election in Petersburg, right? There isn't a state called Petersburg, so I can do that. So the governor election in Petersburg, and they came up with this, that the poll says that the Democrat is 52%, and that the Republican is the other 48. So there are only two people. Nobody's going to take a vote off anybody, and obviously it should add up to 100 unless somebody screws up their ballot. And the internet says that that state is going to go Democrat. Is that state going to go Democrat? Is it 100% sure? No. Do you know a piece of information that is vital to this question that hasn't been given? And I'm getting really quite annoyed at TVs now and newspaper articles and everybody else. Do you know they haven't told you the margin of error? Now, if I say it's 52%, give or take 0.5%, doesn't that mean even on a bad day, the Democrat's going to win because he's got more than 50% of the vote? Suppose it's 52% plus or minus 5%. On a bad day, couldn't the Democrat only get 47% of the vote and actually lose? Do you see why the margin of error is important to who you predicting is the win? Do you know what they should say in this story? Too close to call. I've also heard them in the better places, it's within the margin of error, right? So what that means is if you do a range of that, it could be 47, I guess it could be 57, right? But isn't there a possibility of both things happening, winning and losing? So when they say it's within the margin of error, they're telling you this. Now that number, the margin of error, is the same margin of error I've been calculating. You know, the one that we were showing you. So if you ever see information on TV and they just tell you this, or the other way around, just as likely, will you take that with a pinch of salt? That might not be evidence that anything important's happening. Especially if the margin of error is big, isn't there a really good chance that the other guy, whoever the other guy is, will win? Now, unfortunately, there are some unscrupulous, believe it or not, politicians in the world. Do you know one of the strategies is called voter suppression? Do you know how you can do voter suppression? You flood that area with the Republican's going to win. Every poll has him up. He's going to win by 2%, 4%, 5%. He's going to win. Now, what do Democrat voters do? What's the bother of going out and voting? It's a miserable night. I don't want to do it. So they don't turn up. And if they don't turn up, isn't there a good chance that you've just fulfilled that prophecy? The other guy wins. So you've got to be careful when people tell you somebody's guaranteed to win. If a Democrat tells me a Democrat's going to win, I ignore it. If a Republican tells me the Republican is going to win, whatever it is, I ignore it. Because aren't both those trying to get some voter suppression going? They're trying to make the other side disheartened so they won't bother voting, right? So if you haven't voted yet, you may choose to, if you now think, oh, my guy might actually be winning, and they're just putting out bad polls. I can do polls dead easy that are bad polls. Do you know if I want a poll to be favouring one party rather than the other, don't I just make sure that my sample, the people I ask, favors those kind of people. Just ask a lot more Democrats than Republicans, and don't be surprised if the Democrat wins. Ask a lot more Republicans and Democrats in your sample. Don't be surprised if the Republican wins. So, I mean, this thing is actually happening right now. We are looking at information, or we're being given information that, in my opinion, is very dubious. So just be skeptical. Whoever it is, whatever side is talking to you. Okay, let's return back to the homework questions and see if we can see what's going on. Okay. Well, it looks like a deja vu, but actually, question 6 had hummingbirds, and question 7 had hummingbirds. So it's virtually the same question, just with different numbers. Okay? So I won't talk about it because we've done that question. It's even actually, that's pretty boring. You know, they could have at least made it 95% or something, right? Just add a little variation. And just when you think everything is good, question 8 is another hummingbird question with another 80%. And finally, we get to a new topic. Same question, but just a different story. We've got some medical people here, don't we? We have some nurses, potential nurses. Anyway, want to stick a thumb up if you're going to be a potential nurse or at least something in the medical world?
Dental.
Dental, okay. Anybody nursing, as in hospital nursing? Because dental, I don't think we'd use this information. That's the only reason I'm saying that. Yeah. Okay, then. You're proving me wrong because a lot of my stats students are nursing or they're going to become nurses. So you're keeping it silent. That's what you're doing. So here's the story. Overproduction of uric acid in the body can be an indication of cell breakdown. This may be an advanced indication of an illness such as gout, leukemia, or lymphoma. And they've got that little thing there, and if you click on it, it can even tell you where that reference came from. So this isn't made up data, this is good, real data.
Can I see it?
You can't see it? Oops, I thought I'd done it. Can you see it now?
Yes.
Okay, thank you for picking up. So there's the uric acid story. So if they find a lot of uric acid in your blood test, they're going to say, hey, that's not good. We should be looking for some stuff. You know, an illness that might be causing that. Now, this person has taken 5 blood tests. So it's not big, but you can't take 200 blood samples from one person, right? I mean, that would be cruel, right? So, you know, you do what you've got. You're taking 5 over a reasonable short period of time. You found out that the mean concentration level was 5.35. You know that for a healthy person, sigma is 1.81. So we got all the good numbers there. And question A is asking us to find a 95% confidence interval. Would you agree that this question is pretty standard now? Agreed? So I'm going to go through the working for it as quick as I can so we can get to the latter part of that question. So I'm going to do an X bar plus or minus 1.96 times a 1.81, which is sigma, divided by the square root of 5, and that ends up being 5.35, give or take, coming up. 1.96 times 1.81 divided by the square root of 5, and to 2 decimal places, 1.59. So if I do a lower limit, an upper limit, and a margin of error, the margin of error is 1.59, and upper limit is 6.8, 6.94. And a lower limit is too hard to do in my head. 5.35, take away 1.59 is 3.76. So we would be looking at predicting the true answer to his particular uric acid level as somewhere in that range, right? 3.7 odds to 6.94. Now, can we imagine that we already know what a normal healthy level is for someone? And for a normal healthy level, it's say 3. Won't this indicate then that this guy has got a high uric level? Suppose that the average was 7. Wouldn't this indicate the guy has actually got lower level than the typical? And if the average was, I don't know, 4.9, wouldn't that put him in the range of just normal? So you could be higher, you could be lower, you could be normal. If you're too healthy to ever get it, but when you get older, you'll get all sorts of blood tests. And if you're me and you're a stats kind of guy, I like looking at the details of it, and you'll get your uric level, and they give you a little range of healthy, and they give you your number, and you can compare it, and you can see if you're bigger or smaller than what it should be. So that gives me a chance now to return to, hopefully I'll make it work this time. Good. So the lower limit we got is 3.76. The upper limit is 6.94. And the margin of error was 1.59. That question is getting boring now because it's the same question for everybody. This question is kind of boring. And then they finish with what sample size to get that error. I won't do that question, but won't you go to that big formula that we did earlier, plug it in, and you get 18.2, in which case you would do 19 people, that kind of thing. Right. Question 11 is basically doing a plasma version of that same story. And question 12, another plasma one. We almost done? Yeah. Our last question, 13, coming up. 34 small communities in Connecticut, that's populations around about 10,000 each, have on average X bar 137.1 cases of larceny. Larceny. What is larceny? I'm asking, I've heard the term, but I can't remember.
Like robbery?
Is that what it is? Okay. And the standard deviation is known to be 42.1. And you're going to find, I'm not, but I'm going to talk through it. Aren't we going to find a 90, then a 95 and a 99 using these numbers? So we're going to find a 90% confidence interval using these, a 95 using these, and a 99. And guess what's going to happen? I'm going to make this up. Can you imagine that's what it looks like when you do a 90% confidence interval? And this is what it looks like when you do a 95. And this little guy is what you do when it's a 99. Won't the confidence intervals, we talked about this earlier today, don't they get smaller, right? The interval gets smaller in width when they, oh, darn it, in space. I've had a brain, be dangerous. When you do sample sizes of 10, 100, or 1,000, they get smaller. That's what we talked about earlier. A 99% confidence interval is bigger than a 95, and that's bigger than a 90. Why on earth will you find that? Because when you do the calculations, that's what you're going to get. Why would a 99% confidence interval be bigger than a 90% confidence interval? What's the logic behind that?
Because
Well, so, go ahead.
Ian, what do you think?
because there like would be a bigger chance of the answer like fitting in that interval because it's bigger.
So the bigger you make it, the more likely you are to get the right number in it. Is that paraphrasing essentially what you're saying? Christian, were you thinking the same idea?
Yeah, basically it's the same idea that I was about to say. Yeah.
So you get a question like, if one thing gets bigger, what happens to the other thing? So sometimes as one gets bigger, the other gets bigger. Sometimes as one gets bigger, the other gets smaller. If you're into physics, isn't that direct and inverse proportions? If you want to know the jargon. When both things get bigger, it's direct proportion. And when one thing gets bigger, causes the other thing to become smaller, that's called inverse proportion. You do not need to know those terms in statistics, but if you're into physics, maybe that'll help you see the relationship a bit better.
The n equals at the bottom, is that supposed to be 1,000?
Yes.
Okay.
Okay, I'm going to leave at this point. It's a little bit early, but I want to get your tests all done. Well, they're done, but I want to get your grade together, and then I have to send out your emails. So if anybody is here who has not done the midterm, will you hang about for 5 minutes so we can figure out what the heck to do?